In this video, I'm going to teach you a method you can use to easily complete your own physics research. More precisely, I'm going to discuss how to computationally test and derive the nature and proportion of dark energy within the universe, which is similar to what Perlmutter did in 2011, which ultimately awarded him that year's Nobel Prize in Physics. All you'll need to complete the types of projects shown in this video are a computer and an internet connection, and judging by the fact you're currently watching this video, I'll assume you have both of those. So without further ado, let's firstly discuss the theoretical considerations which we'll eventually be testing. It has been known since at least 1929 by Edwin Hubble that almost all objects in space are moving away from us. This is inferred through the redshifting of light from distant objects indicating their recession, and this effect isn't special to Earth. No, we know that every point in the universe is moving away from every other point, like the fabric of space-time itself is expanding. You can think of the universe as the surface of a balloon. As it's blown up, the space between every point grows larger. The relation between the recession velocity, or speed, and distance from us is given by Hubble's law, where h is the Hubble constant, which quantifies how fast things move away from us at each distance. Unfortunately, the name Hubble constant implies it's static and unchanging. In reality, this constant changes over time, gradually increasing. Physically, this means that the velocity of recession at a particular distance increases with time, which is a complicated way of saying that the space-time expansion is accelerating. But what is causing this acceleration? Gravity is always attractive and should be pulling all objects closer, so whatever it is must be stronger and act opposite to gravity. Modern science is still not sure what is causing the accelerating expansion, but nonetheless have labelled it as dark energy, a mysterious substance which we're yet to find. But we know it must be there, otherwise gravity would cause the universe to collapse and light from stars would all be blue shifted instead. Dark energy is the crux of the Perlmutter analysis and is what we'll be trying to learn more about with this project. The evolution of the Hubble constant can be derived from Albert Einstein's general theory of relativity and manifests as the Friedmann Equation. To save time and needless explanation, I'm just going to write it down in this form. You can see on the left we have h squared, where h is the Hubble constant at the time we're interested in. Then on the right we have h0, which is the value of the Hubble constant today, around 70 kilometers per second per megaparsec. I'll explain those units in a little while. We also have these omega terms, which can be thought of as the constituents of what makes up the universe. Omega m is the matter density, and omega dE is the dark energy density. There's also k, the curvature, c, the constant speed of light in a vacuum, and finally, a, the expansion factor of the universe at the time interested. All these terms might look intimidating, but really they're not. H and h0 have units of kilometers per second per megaparsec, which physically means that every megaparsec away from Earth you look, stars and galaxies move away by a further 70 kilometers per second. A megaparsec is a large unit of distance equivalent to around 3.26 light years. For the next part, I'm going to briefly assume a flat cosmology, so that k equals 0, which is a good approximation and makes explaining the important terms easier for now. In this cosmology, the omega terms are simply the proportions of matter and dark energy in the universe. For example, if omega m equaled 0.9, that would mean that 90% of the energy in our universe is locked up in the form of matter. This would also tell us that the other 10% must be in the form of dark energy, since we are assuming the entire universe is made up of only matter and dark energy. A quick aside, matter here includes both regular and dark matter. So we can relate omegas using the simple intuitive equation that they must sum to equal 1. Here I've also neglected energy contributions from radiation, which as we'll see is a good approximation for the present day universe. A is the scale factor and describes how the expansion has grown. We arbitrarily set A equal to 0 today, and so that A is greater than 1 in the future and less than 1 in the past. As an example, the distance between two galaxies could be 10 megaparsecs today. In the future, when the universe has expanded more due to the dark energy, the physical distance could have increased to 20 megaparsecs. Here we see that A equals 2 at that point in the future, since the physical separation has doubled from today. So A is the scale factor and can be used as a variable instead of time. Interestingly, when we observe light from distant stars, we are already seeing how they looked in the past. So the redshift at which we see them is related to how long ago they emitted the light we are detecting. So redshift is also a time variable, and related to the scale factor A by this formula. As a recap, in the future, A increases and Z, the redshift, decreases. The reverse is true for the past. Okay, so now we understand the basics of the Friedmann equation. It's going to be this equation which we are going to be applying to datasets from type 1a supernovae to try and deduce the values of omega m and omega dE, to then know the proportions of matter and dark energy in the universe. Type 1a supernovae are violent explosions in space, which happen when two stars are orbiting in a binary, and one of them happens to be a white dwarf and the other is a star in its red giant phase. White dwarfs are dead remnants of stars and are superdense, only being held up by electron degeneracy pressure. Essentially, quantum mechanics forbids electrons from occupying the same physical space due to them being fermions and the Pauli exclusion principle. And it's this which is all that's stopping the star from collapsing. In a Type 1a supernova, the white dwarf accretes matter from its companion, gradually getting more massive. The star eventually reaches the point where its own gravitational weight force is too strong and even overpowers the electron degeneracy pressure holding it up. The white dwarf collapses and violently explodes as a Type 1a supernova. The key thing about these explosions for us is that to first order, they have a constant peak brightness. On screen now, a graph showing the brightness or luminosity of Type 1a supernovae, which all peak at around the same point. This is extremely useful to cosmologists and astrophysicists, since it means Type 1a supernovae act as standard candles. I want you to imagine you had a candle or a torch or something which you knew exactly the brightness of. You have a number quantifying the brightness. Now if this light source were to move away from you by some unknown distance, you could then very easily work out that distance by measuring the light amount or flux you receive, and as light flux follows an inverse square law, find out exactly its distance from you. The same concept will be applied to these supernovae to work out their distance from us. I hope you can see where this is going. We can use that inverse square law and the fact that distance is also speed multiplied by time to fit a theoretical physical distance from the Friedmann equation to Type 1a supernovae light curve data. We can also easily measure their redshift. Then, by statistically iterating over different combinations of parameters, we can find the best solution for the amount of dark energy in the universe by seeing which set best fits the data from the supernovae. This may still seem quite confusing, but don't worry, we'll get there. The best way now might be to just show you what I mean in practice. In order to do what I just mentioned and explained, we're going to need a few things which altogether cost the low price of nothing, provided you already have a computer and internet. First of all, we'll need data from Type 1a supernovae, and luckily for us, there's tons of free and reliable data sources, which has what we'll need. The website I'll be using to get my datasets is the Supernova Cosmology Project website. Simply follow where I go on screen, and you can find lists of downloadable data sets. In particular, we're going to need data on redshifts and brightness, which is usually given in magnitudes, as well as any errors on those values. Save them as a text file and pay attention to information like the brightness correction factors, which will be important later for conversions. Next, in order to use and test models from the data, we're going to need to do some computer coding. Don't worry if you've not done much before. Completing or at least watching a project like this can be beneficial to learning. Feel free to use any scientific computing language you want. I'm going to be basic and boring and go with Python. You'll want to download a Python interpreter or use something like a Jupyter Notebook in order to execute Python scripts. Finally, the last tool I'm going to recommend for now is actually AI. Coding can be tough, and being a physicist, not a computer scientist, my programming can often leave much to be desired for. I find that working with AI to help spot and fix errors in code, make it more efficient, or even suggest new ways to proceed can be invaluable. So load up and have some kind of AI on standby just in case. I'm going to go with ChatGPT, but use any AI provided it's smart for data science. So don't even think about using Snapchat AI or any other brain-dead machine. Once you've downloaded your data, we're going to firstly want to get Python or whatever language you're using to be able to read it and use it appropriately. I've created arrays for the different variables from the supernova data. You can see that I'm able to plot things such as redshift against magnitude and get what you'd expect. I'm going to go a bit quicker through the coding and really focus on the key parts you'll want to create and the results you should expect. Remember to use the AI if you run into errors or check online help guides for particular libraries and functions. The first thing worth mentioning is that the matter and dark energy proportions aren't the only unknowns in our analysis. Really, the present-day Hubble constant, the peak luminosity or brightness of Type 1a supernovae, and things such as the curvature k, if you choose to include it, are also free variables. Now, what you can do is make the small distance approximation shown here to minimize to find the peak brightness and then use it in later analyses, or you can just assume it from literature. Typically, you'll want to assume h0 as around 70 and make sure that all other values have units which work together. So know your conversions. Anyway, remember the scale factor a we used before? Well, that's essentially our x variable. Since we have the redshift measured from the dataset, the physical distance to a supernova in the future is a multiplied by its current distance, because a equals 1 at present. We can take this physical separation and substitute it into the expression for flux from peak luminosity, and then use the flux magnitude conversion equation to get our theoretical brightness for supernovae at each redshift into magnitudes. Here I've simply set up my model which I'm going to be testing, and I've set the matter and dark energy densities as the free parameters which I want to find. So think of it as we're creating a mathematical function which you can give a redshift of a supernova and it will spit out its brightness measured on Earth. The key is that within that function there's the matter and dark energy densities which we don't know and want to find. So we can check the output for different values of those densities, and whichever matches the dataset which we downloaded the closest is likely the distribution of dark energy in our universe. The function ends up being this horrible mess which involves integrating the Friedmann equation and using the distance light travels in an expanding universe using c over h0 to find that distance, as well as using the aforementioned luminosity flux and flux magnitude relations. It looks nasty and is impossible to solve analytically, but Python will be able to handle it. This is all from the theory, so feel free to check out the links to papers regarding it in the description, or do your own research if you'd like to learn more about calculating distances in cosmology. But now I'm going to move on to talk about a really important point: the statistics. It's all well and good discussing in theory that we want to find the best combination of parameter values in order to match our model to the data. Alas, it is never that simple. As scientists, we require ways to quantify the goodness of a model compared to the data, and the parameter values associated to that model must have associated errors in order to be acceptable in any analysis. One way to quantify the goodness of a fit and find errors is using the chi-squared statistic. The chi-squared is given by this formula, which may look complex, but really it's very simple and intuitive to understand. Let's look from right to left and top to bottom. YMI is the model value of the ith data point. I is just the point we're interested in. It could be the third data point, for example. And so in our analysis, this variable is simply the predicted brightness of the ith magnitude point from our model at that redshift. Then YI is the actual brightness recorded of the ith data point supernova. You can see we're subtracting one from the other, so if the theoretical model and actual data point are close, this difference will be small. Conversely, if they differ by a large amount, the subtraction will leave behind a larger value. We obviously want to find models which closely agree with the data, so having smaller differences is better. In the formula, we then square the difference, which really just gets rid of any negative signs, so the difference is always positive. We then divide this by sigma I squared, which is the error of the ith data point squared. We square it in order to match the numerator, and importantly, chi-squared assumes a Gaussian or normally distributed errors. So the errors on a measurement must be randomly distributed in a normal distribution in order for chi-squared analysis to be valid. Often this is the case, but it isn't always. For our analysis, we should be okay. You can always make a plot of the errors from the data in magnitudes, and see they do in fact follow a normal distribution. This is also why I opted to convert the model to magnitudes rather than the data to flux, as flux and magnitudes aren't linearly related. So Gaussian magnitude errors may not necessarily correspond to Gaussian flux errors, so you need to be careful. Nonetheless, this looks all good for our data. Finally, in the chi-squared, there's this capital sigma symbol on the left. This just means sum over all data points. So we find this difference, divide by the error, and square it for every data point, and then sum them up. So qualitatively, if the differences between the model and data are small, implying a good agreement, the chi-squared is also small. And if they disagree a lot, then the chi-squared is larger. Therefore, we can say that the best combinations of parameter values lead to a low chi-squared. The number of degrees of freedom is your number of data points minus the number of fitting parameters, and dividing the chi-squared by the degrees of freedom gives the reduced chi-squared. Then, if the reduced chi-squared is close to 1, we have a good fit. Much greater, and it's a poor fit, and much less implies overfitting, where the error may not be Gaussian or the data inappropriate for chi-squared. Let's look at a quick example for something much simpler than the supernova and cosmology data, so that we can understand chi-squared and how it's used in scientific modelling. I'll show this in Python so that you're free to read and use parts of my code later if you so wish to. Here I've created arrays of data. There's X and Y data and also Y errors. These are purely made up for this example, but would correspond to the supernova data in our project. So redshift would be X and magnitude is Y, for example. You can see if I plot and label this data, it looks to follow a straight line. Intuitively, you would think therefore to try and model this data using a straight line model, something of the form y equals mx plus c, where m is the gradient and c is the y-intercept. This is analogous to the supernova data, where the plot shows the sort of curve shown earlier, and the model is far more complicated, involving that nasty integral and combining all those other equations. But fundamentally, these are the same concepts. So in Python, I'm going to define a function which is a straight line model, with missing values for m and c. So m and c are our free variables which we want to find, just like the dark energy density in our project. I can use the curveFit function in Python to find the best fit m and c shown here, or more usefully, I can create my own way of doing it using chi-squared, which I'll show now below for better understanding. You can see I define that chi-squared equation in Python and work it out. For the best fit, we want the smallest chi-squared, and so this data analysis method is known as chi-squared minimisation. Here, the reduced chi-squared we get is around 1.3, which is close to 1, indicating a good fit using the straight line model. Python is able to optimize the values of m and c, giving m around 2 and c around 0, but slightly negative. If I now plot this best fit straight line on the graph with the data, you can see it fits it quite well. Most of the points within their error sit on the line, indicating a successful chi-squared minimization. Hence, we have subsequently numerically worked out the best fit m and c. But we still need their errors. In physics, all derived values must have an associated error, and we can do that using chi-squared as well. The one standard error range includes the region around the chi-squared minimum, which contains the 68% confidence limit. For two parameter fits which may have correlated error, this corresponds to 2.3 units above the chi-squared minimum. This will be easier to see using a plot. So here's one from a chi-squared analysis I did using real data I had previously collected from a muon detector I built. Again, I fit a straight line graph, but obviously the best fit values were different. You can see the chi-squared 2D region, where the darkest part is the minimum chi-squared, and so corresponds to the best fit parameters. That is, c around 10 and m is around 55. The white ellipses show the regions containing the different errors, where the chi-squared value increases by 2.3 units for the one standard error range. Then in order to find the error or uncertainties on the parameters, you can simply read off where the boundary of this ellipse strikes the axes. So here, I report that c is 10 plus or minus 70 and m is 55 plus or minus 5. Obviously, we can apply this same method to our supernova analysis, with many more parameters to find their values and errors. Although it's worth noting that multi-dimensional chi-squared spaces are difficult, if not impossible, to draw in our simple 3D world. So that's the basics of chi-squared minimization, and next we will implement it into our cosmology project to find parameter values and errors. You can see I define a function called magmodel, which instead of simply being y equals mx plus c, it's the brightness magnitude from Redshift done over a few lines of code. Then, using almost exactly the previous code, just with different variable names, I can use the built-in chi-squared curve fit to find the best values for the peak luminosity in ergs per second, and also the matter and dark energy densities. Similar to the example, I can use Python to plot out our function, using the best fit parameters for peak luminosity and dark energy density. Here's that plot with the actual supernova data we downloaded, and as you can see, it fits quite nicely. So that the blue line is really the plot of that complex and insufferable equation from theory, shown before, which implies the data supports that theory. The chi-squared value for this best fit model was around 0.98, also backing the theory. I can use the method shown in the example to find the error range on the fitting parameters too, and then if I redo the plot on Python and include those ranges, you get this graph. The only difference here is now that any functions which sit between those two dashed lines lie within one standard error of the best fit set, and so are statistically feasible alternatives to the best fit line. The supernovae points are the faint red points, and again, most lie or are within one standard deviation from the best fit range. If you don't believe me, then I can show it's true by including a subplot which plots the normalized residual of each supernova data point from the best fit line. Essentially, this shows how far they differ from the best fit theoretical function and are normalized by how large the error range is on the measurement. We'd expect this to follow a normal distribution, and if I were to count up and plot how many of these points lie within one standard error of the blue best fit line, I'd get around 68% as expected. 95% would lie within 2, and so on, meaning chi-squared and all its assumptions were likely valid for this data analysis. So I hope you can see how scientists are able to statistically test theoretical models using datasets. But physically, what does this mean? Well, getting an omega dE of around 0.7 implies that around 70% of the universe is dark energy, and the other 30% is matter, which means we're living in a dark energy-dominated era. You might think that's quite strange. Everything we're made of and interact with is matter, and not dark energy. So how can it be that dark energy makes up the largest proportion? Is the equation wrong? What's going on? The answer goes all the way back to the beginning of the theory with Hubble observing the recession of galaxies. He observed that on cosmic scales, larger than galaxies, objects accelerate away from each other, if you remember. Galaxies should attract gravitationally, so the fact that something is more powerful and dominant than gravity, which is caused by the matter, implies that something else is more abundant or energetic than all of the matter in the universe at our current epoch. Remember, we coined this something else as dark energy, and so really we expect dark energy should make up the largest proportion of the universe from the very beginning, and that's exactly what we found using data from light curves from supernovae. Isn't that fantastic? We've been able to verify that we live in a dark energy-dominated universe at the current time using freely available data and a little bit of coding and statistics. I think that's crazy, to be honest, and the Nobel Prize Committee clearly agreed as they awarded Perlmutter the 2011 Physics Nobel Prize for this sort of research. The project doesn't stop there, though. There are so many more ways and things you can do to extend and build upon this foundation. Remember, we made quite a few simplifying assumptions in the theory. For instance, we assumed k was 0. This isn't necessarily true, and so you could choose to rewrite all of the theory and functions, including k as well, as another free parameter you need to minimize. You could also include h0 as something you want to deduce instead of just assume. Alternatively, you might want to investigate the nature of dark energy further. Our model is known as the lambda CDM model. Lambda means cosmological constant, and CDM meaning cold dark matter. The cosmological constant is the form of dark energy, which is constant throughout time. Yet, there's no reason why you couldn't also have it evolve and change with time, like with the matter density, which obviously decreases by a, the scale factor, cubed, as the universe expands, as volumes increase and depend on length cubed. Incidentally, this is also why I chose to ignore radiation density, as that decreases with a to the fourth power, as there's the decrease with increasing volume from expansion like with matter, but then another factor of a from the redshifting decreasing the energy of radiation. But with dark energy, you don't need to keep it constant. For example, shown on screen is some further analysis I did where I assumed it evolved and had an equation of state parameter called W. Later, I replaced W with two parameters WO and WA to test more complex models. These are known as quintessence forms of dark energy, and what I found is they centre on the lambda CDM model, but do allow for some evolution and change within the dark energy density over time. One thing you need to be careful of is that as you increase more parameters for your chi-squared minimization, the amount of degeneracy increases. By this I mean the amount of combinations which could fit the data goes up drastically with more free variables. This leads to solutions which could be unphysical or the chi-squared not working at all. This is of particular concern if you choose to fit both quintessence models and a non-zero curvature k value simultaneously. So I'd be careful when doing so. Try and keep the number of parameters to 4 or 5 max to avoid really large areas of minimum chi-squared which aren't useful. Another issue comes with the computing power required when you test more complex models. The chi-squared method I showed on Python uses a grid search to inspect a large region of parameter space and find the best combination. Yet, this becomes infeasible as the number of parameters increases. For example, with 2 parameters, it will be inspecting the surface of a square. With 3, it will look at the volume of a cube. 4, it will be searching through the 3D volume of a tesseract, and so on. In order to keep computing times relatively short and avoid killing the kernel, you can save time not inspecting non-physical or non-useful areas of the chi-squared space by using less automated techniques. This video is already quite long, so I won't go into too much detail, but for searches with more than 3 or so variables, you'll probably want to use something like a Markov Chain Monte Carlo or MCMC technique, like the one I've been using in my Quintessence fits in the last few clips. This unevenly surveys the space and focuses on regions where chi-squared is lowest, which saves a lot of time, but opens a whole new can of worms in terms of the statistics and errors. Another cool way you could extend this project is to use different datasets or sources. For example, cosmic microwave background, CMB, or Baryon Acoustic Oscillation, BAO, data. Similar to how Type 1a supernovae act as standard candles, CMB acts as a standard ruler, and so can also be used to test cosmological models using functions based on the harmonics and frequencies of radiation contained within the CMB. Again, this data is freely available and is compatible with Python. I'll show on screen a way to access and download the things you need, as well as some of my own results from testing simple quintessence models with it. This stuff is more advanced, and always requires non-automated methods in order to compute, due to how power-consuming it can be, but I suggest giving it a try yourself. Overall, I hope you can see the endless possibilities for where someone could take this project, and how big of an achievement research like this is to physics and cosmology, which led to a Nobel Prize being given out for it. It's really a lot of fun, and a great way to practice scientific computing skills. With every new data release, you can further refine your estimates for various universal parameters, giving this project longevity should you wish to do so. Make sure you leave a comment letting me know if you try any of the data analysis yourself and any other ways you can think of to add to this project. Also, feel free to comment or drop me an email if you'd like more technical help doing this project. I'd be more than happy to assist. If this video does well and enough people want it, then I might consider creating a GitHub or something where I can provide you guys with the code I've created. So look out for a pinned comment or something. With that being said, the stuff here is quite advanced and difficult, so good job for making it this far. If you've enjoyed the video, make sure you leave a like and subscribe if you haven't already. It really does help me out, and I'll see you next time.